Hello everyone, I am Sneha. I am going to talk about the HST COS Ultra-Violet High Resolution Survey of 307 DA White Dwarfs. So this I did in collaboration with Boris and Pierre at University of Warwick. So what is our motivation of doing this survey? So the objects that we have selected are part of ongoing HST COS Ultraviolet snapshot survey. So where the main aim was to investigate the fraction of planetary systems around the young white dwarfs. So already there are few papers interesting coming from this survey. Now, what we have mainly used in this survey is the HST COS data, which is a high resolution data which we have used, and it covers the Lyman alpha region. And the main aim of this work was to check the internal consistencies between the UV and optical derived parameters, and also correlate the presence of planetary debris with other basic parameters. So why we are motivated to do this work, because the earlier UV studies, like there were few in 2000 and 1990s with IUE and fused data, so where they were mostly focused on very hot white dwarfs, such as temperature greater than 50,000 Kelvin, and there were very less number of stars. So this is first large systematic survey of white dwarfs in UV DA white dwarfs, and which covers like the intermediate temperature range from 13,000 to like 30,000 Kelvin. So now what we have done in our fitting method, so we have used coaster models which are updated, and we have included the improved star broadening profiles from Tremblay and Bergeron, and then we have used Gaia EDR3 parallaxes. And what we have done while fitting, we haven't done any normalization, rather we have fit the absolute fluxes that we got from HST observations. And while fitting, we have masked the interstellar and photospheric lines. And the another thing important is we have used different two different white dwarf mass radius relations. So first is the Montreal, which assumes like CO core for the entire mass range from 0.2 to 1.3 solar mass. And it assumes a common envelope composition like hydrogen, which is around 10 to the minus 4 solar mass. Whereas we have another mass radius relation from La Plata group, which uses different core composition for low mass, like it's helium, and for intermediate it is CO, and for higher it is ONE core. So they also assume different hydrogen and envelope. And now what we wanted to check is how this, using these two different mass radius relation in our fitting, it gives different results. So this is the one example of a star in our survey, white dwarfs. So you can clearly see the red is the fitted model and the black is the observed one. And you can see that we compared that with other results. And the red one is the fit from the Montreal group, and the gray one is the fit from the La Plata. And we see slight differences in both the obtained parameters. However, we see that they agree with other studies. So another important thing is we report the first spectroscopic observations of around 49 DA white dwarfs that were discovered by Gaia. So this object did not have any other spectroscopic observations and parameters. Now coming to once we have got all the results from the UV survey, what we did, we compiled all the previous literatures because we wanted to test the consistency between the optical and UV parameters. So the most of the studies we found, they are from the optical spectra, like the Janinas and Koester's supernova progenitor survey. We also have a few older studies where they have used older models and different methods. So now, in case of photometric estimates, which we have compared, we have used mostly Gaia for comparison, where Nicola's paper has given the parameters. And then we have used PanStar's data and fitted the parameters using the updated models. So all these techniques, they have used a mixing length theory of 0.8, and they all use the star broadening profiles, except few papers which use older models, like such as the unified theory of star broadening, the VCS profiles. Now, most of these optical spectra that they fit is they mostly use the optical observations and fit the normalized Balmer lines with continuum set to unity. And in case of one observations like study Detlef, There they have used the UV data from our HST COS snapshot survey. But since that time parallaxes were not available, they fixed the log G to optical values and varied the temperature to determine the best fit value. So thus we also compared with that how the different methods can give you the results. So another thing is our method you can say it is comparable to the photometric technique, because they are also using parallaxes and mass radius relation from Montreal, and then reddening values from the 3D stellism, which is shown here. So now after collecting all the published results, we used basically Montreal White Dwarf database to collect these results. And also we looked at some other, because this helped a lot in collecting all the results and plotting it. So this is examples of 3 of the stars in our sample, and you can clearly see that the parameters they span very wide range from different studies. And so these are the best like model fit to some of the stars. Now also we have a few stars like here, which I told you, which have first spectroscopic observations. And here you can see these are only the photometric estimates, the right side plot. So now coming to the model fit to some of the other stars which were showing some problem in the Lyman alpha region. So you can clearly see that in the Lyman alpha region, the model does not fit well. So it means like that some of the stars can be double degenerate. So in fact, we found one of them is a known double degenerate in our survey. And another, like the lower one, you see it is a composite system, but it is not classified as a double degenerate or something in earlier study. But still we see that the Lyman alpha is not fitting well. So thus UV observations can help in identifying these outliers. And also you can clearly notice the photometric estimates, which is shown in green circle, they deviate a lot with other parameters. Now coming to the overall sample, the distribution in temperature log G plane, and the red is the model from the La Plata group, and blue is the one from the Montreal mass radius relation. And you can clearly notice the difference below the lower mass, because they assume hydrogen envelope of around 10 to the power minus 3 solar mass, whereas at 0.5 to 0.6 solar mass, the hydrogen envelope is same in their models. So in fact, in study by Romero et al., they have shown that if you do not consider the dependence of hydrogen envelope in your models, it can lead to incorrect like estimation of masses. So that's why we should consider this different hydrogen envelope in our fitting also. And the yellow ones which you see are the fit that we derived from the La Plata Montreal mass radius relation, and the black one are the Montreal. So we clearly notice that there is, in the low mass end, there is large difference in the number of stars. So this is the mass distribution of these white dwarfs that we obtained, where the red one is from the La Plata and blue one is Montreal. So here you see that overall the mean mass is 0.6 solar mass. However, the main peak of the mass is at around 0.53 solar mass. And also we notice a broad secondary peak, which comes at around 0.76 solar mass. Now this secondary peak, we know that these are from earlier studies. They say that this secondary peak can be coming from binary mergers, or due to a different like assumption of the initial final mass radius relation, where they found that there is a flattening at around 3 to 5 progenitor stellar mass. And then also it can be due to crystallization. But since in our sample, most of the stars are above 10,000 Kelvin, and they are like less than 1 solar mass, so we don't think crystallization can entirely explain the secondary peak. Now this is the mass distribution comparison with earlier studies, where the number of common stars was a bit larger, like with Janina studies, which is an optical survey, and then we have supernova progenitor survey, and Nicholas study, where the Gaia data was used to derive the parameters. So we can clearly see that all the optical studies, they report a mean, like this main peak, it comes at around 0.6 solar mass, whereas from the UV, we are getting it around, it's a bit lower, like around 0.53 solar mass. Now coming to the upper one, which you see the green. So this is the Quester survey, but they used line broadening profile of VCS, which is different compared to the updated ones, which is shown in the black, which we have fitted. So you can clearly notice the difference in the like line broadening profiles when you change it, and the parameters are different. So now also we checked the mass distribution, how it varies with sample selection. Like we took the distance at 100 parsec, 80 and 60 parsec, and we can clearly see that the distribution remains overall same. However, the number of massive white dwarfs, it decreases at lower distances. Now this is our comparison with spectroscopic estimates. You can clearly see that the temperatures are deviating by 10% in case of Janinas, whereas other survey, it is like around 3% deviations. Now, overall, we can say that from the UV, we found a lower T effective and log G compared to the published estimates. And this is comparison with photometric estimates, where the symbols that you see here, different pentagons and red, they are the outliers that we identify in our survey. So we classify those as outliers which have temperature difference greater than 10%. And we found that around 7% are outliers in our survey. Overall, like the Gaia and Pan stars, it agrees better. However, in the parameters that are published in Montreal White Dwarf database, we found slight differences, like the temperatures are lower in the Montreal White Dwarf database. So this you can clearly see that the arrow marks, it points the values. So from the Gaia and Pan stars, we see that the UV values are lower in log G and T-effective, whereas in Montreal White Dwarf database, they are higher. So this is our overall outliers, and we see a systematic offset of 2% in masses in the log Gs. And these outliers, what can be? So the red dots which you see here, these are actually the known double degenerates. So we see that some of the double degenerates fall in the outlier region. And the magenta triangles which you see here, these are known white dwarfs with circumstellar disk. So this also we see that they are somewhat not coming in the outlier. So they are hidden in the main. So we can't clearly classify them based on the differences between temperature and log G. Yeah, so this is the first large statistical study of TA white dwarfs. And we are providing first spectroscopic parameters of around 50 white dwarfs. So the mass distribution, we see that the main peak is slightly lower than the optical studies. And also the temperature and log G determined from UV spectra, they are on average lower than optical and photometric results. Yeah. So thank you.
Very nice talk. Questions?
So when you're fitting the spectra, you're constraining the flux from the Gaia parallax. Is that right?
From Gaia?
You're constraining the flux from the. You're not fitting normalized spectra.
No.
Is that right?
So
is your So is your mass mainly coming from that constraint and not the shape of the Lyman line?
No, actually we are fitting the absolute fluxes, and we are taking the parallaxes and constraining the radii, and that is fitted, like the models are scaled according to the radius and parallaxes, like the distance that we are getting from it.
Okay.
Yeah.
Oh, so I have a related question. So, similar to fitting in the UV, how do you deal with an extinction?
Yeah, we have actually considered rendering in our, we have used Fitzpatrick extinction law, and we have corrected for that, like the observed fluxes. We have corrected that and then fitted it. Yeah.
I'm sorry if I'm asking a question that you actually addressed, but what fraction of these white dwarfs have previous like chemical abundances in the literature from, say, optical spectra? Do you have a plan to compare whether the results agree?
Okay, so Deathless paper, they checked 85 DA white dwarfs, and they found around 27% of them, they have like signatures of planetary debris. But others we haven't yet checked, like we will check it. The outliers and other, like we'll check individual and do comparison with the optical, whether they have this thing in our future study. Yeah.
Any other questions?
A couple of slides ago, you said that some of the outliers could also be magnetic, maybe.
Yeah. Actually, I checked them in the Montreal database, and they're classified as magnetic. Some of them lying there, 1 or 2 of them.
I guess a test that could be done, since you have the COS spectra and some of these go down to 10,000, would be to fit them with radiative rather than convective models and see if that brings the agreement closer.
Okay, then we'll look into it. Thanks.
Maybe.
Other questions? Okay, if not, let's thank all our speakers again for the session.